Our next speaker is Erich Peitzsch. Erich is a research physical scientist at the U.S. Geological Survey at the Northern Rocky Mountain Science Center in West Glacier, Montana. Before working for the USGS, Erich was a ski patroller, an avalanche forecaster, which he still does some work in, and a longtime avalanche educator. He studied at Montana State University doing some really interesting work on avalanches and climate. And I'd also just like to put in a plug for Erich as bridging the gap between research and a lot of the operations in the United States. He's done a great job engaging the avalanche operations and doing quality research from those collaborations to benefit us all. So he's going to talk a little bit about some of that work. Please welcome Erich Peitzsch.
Thank you. All right. Thank you, Ethan, and thanks all of you for being here, coming back from the break. I still hear people talking. I'm gonna do as my kids' teachers. If you can hear my voice, clap once. If you can hear my voice, clap twice. See, gets everybody. All right. Yeah, thanks everybody for being here. So, more of this. We're going to talk about avalanches and climate, and when I talked to Jason about my topic of this presentation, I said, yeah, I'll talk about wet slabs, and so I lured him in with wet slabs, and now I'm going to talk about avalanches and climate too. So we're going to fit two studies into one presentation. Let's hope this works. First, I want to thank my amazing co-authors on all of this work that I'll talk about today. Many of them are here in the audience, so if you see them, give them a pat on the back and say, thanks for helping Erich. He really appreciates it. And I'd like to thank the USGS Climate Research and Development Program for support financially. All right, so some of the questions that we wanted to answer here. What are the climate drivers of large avalanche cycles in Colorado? Last year, Ethan gave a presentation here at CSAW about avalanche frequency after, in the context of the March 2019 event that we're probably all very familiar with. So I'm going to talk about the climate drivers of avalanche frequency and probability in Colorado. Then we're going to talk a little bit about the weather and snowpack patterns of two midwinter wet slab cycles, not in Colorado, but in Montana and Idaho. And that's the sort of more of this component of the presentation title. And we'll talk more about that as we move along. And then finally, how did those events actually compare to historical climate and other similar warming events in the past 30 years? All right, the March 2019 cycle, we're, again, all probably very familiar with this statewide, very large in magnitude and spatially extensive avalanche cycle. We use tree rings to extend the avalanche records, so we've heard a lot about keeping good records. And here in Colorado, you all have pretty decent records, in the context of the US. When we talk to our European colleagues, they're like, oh yeah, we have records from the 1700s, and I'm super jealous. We don't, so we had to use trees to help us tell the story. And we cut cookies from dead and down trees, so we didn't cut living trees. And there were, of course, many, many trees to sample from after that cycle. We took those back to the lab, looked at them, and we have our oldest records of trees actually date back to the mid-1300s, but statistically we need more than one avalanche signal in a given year to call it an avalanche year. Regardless, we were able to classify avalanche years all the way back to 1806. And we'll get into the frequency part in a second here, but I just want to sort of touch on how destructive this cycle was. And on the maps here on the right, we actually looked at changes in ground cover. So basically looking at avalanche paths, the, quote, greenness in avalanche paths, where you can imagine if you have a lot of trees, it's really green. You take out those trees, not so green. So, for example, the map on the top there on the right is the Conundrum Path just outside of Aspen. And there was over 15% ground cover change in just that avalanche path. So that avalanche path, the trees, the tree cover, the ground cover changed pretty dramatically. And again, that happens statewide. All right, so we found that big cycles like this in Colorado, the plot on the top, and there are going to be figures. You won't be tested on them, but they're super easy. They're time series figures. So we're just going to look at time on the bottom axis here, and on our y-axis, we're looking at avalanche probability. So first, I actually want to point out these gray lines are not the trend line of avalanches. These are actually our sample sizes. So you can see that our sample sizes way back in time, we didn't have many samples, but the sample sizes rises pretty substantially, especially by the time we get to the mid-20th century. So that's not our trend line. But what we did find, and Ethan talked about this a little bit last year, but I want to remind everyone that the probability of big cycles like that happening is actually decreasing, specifically since the 1900s. So from the 1800s to 1900s, we didn't have as many samples, so we focused on the 20th century and the first part of the 21st century. So from 1900 to 2019. So you can see that there is a general decrease in the probability of a cycle like that happening. Statewide cycle, again, talking about big avalanches across a big area. But we can see the 2019 spike right there. So it's not like these avalanche cycles are going to disappear. They're not. But they are going to potentially, at least from the data that we have, we've seen that they're going to become less frequent. So that actually plays with our minds a little bit, because in the lifetime of an avalanche professional, we may not see a cycle like this. So I think the 2019 cycle was really incredibly destructive and stressful and not good in many ways. But from an avalanche professional perspective, it was really effing cool. So we have those data. We were able to use them. And then we took them and looked at climate drivers. So let's take a look at some of these here. We're looking at a changing snowpack through time. One thing to keep in mind is that we have something called non-stationarity. What that basically means is that climate variables, for example, the mean, so the average, roughly the average, is actually changing over time. Stationarity means that the mean stays the same. Non-stationarity means that it changes over time, so that average changes over time. So what that means practically is that what's happening now, what's, quote, normal now, may not have been normal, or may not have been the same normal, say, 30 to 50, however many years ago. So we kind of showcase some of that here. In the period of 1900 to 2019, we actually see a general decrease in snow water equivalent, and that's how we're measuring our snowpack in this study. And that was roughly around -6 millimeters of SWE per decade. And that's a statistically significant decreasing trend. So then we took a look at it and we're like, all right, if we have non-stationarity, let's take a look at the mean and how does it change. And we were able to break it up into 3 periods in the 20th and early 21st century. The early period is 1900 to 1940, mid is 41 to 88, and the late is 89 to 2020. You can see here, again, this orange line is the snow water equivalent of in our avalanche years, so only avalanche years throughout the whole record. And you can see that it basically decreases. So this is a clear indication of non-stationarity, and it almost looks like, in some ways, there's a step change here. But you can see in the late period that it decreases pretty substantially. So again, another way to look at it here, and this is our April 1, so this is our peak SWE of the whole season. So we're looking at how big our snowpack is. And so coincident with that decreasing probability of big avalanche cycles, we see a decrease in snow water equivalent. And the orange line is sorry, this thing's falling off my ear. I'm not as good as the folks previous session, sorry. But we can see in avalanche years, there is a greater change during those years, or decrease in our snow water equivalent per decade than there is in the whole period. All right, so changing climate drivers. And the panels on the left, we can see, again, if we look at the early, mid, and late periods, we see changing climate drivers in terms of snowpack. In the early periods, it was driven primarily by big snow years, so big avalanche years driven by big snow years. And that sort of changed gradually from the early to mid. And then in the late, you can actually see that we have below average. So again, the black line is our average. The orange line or the red line is our mean during avalanche years, and you can see that during avalanche years, it's below, our snow water equivalent is below average in December, but way above average in March. So instead of big avalanche years driving, or big snow years driving big avalanche years, what we actually see is less snow in early winter, so like December, followed by really big storms in March. And an example of that was in 2019, where we had here, a weak layer develop in the early winter season. Subsequent storms throughout the season, it wasn't a particularly huge year, but then enough where that storm in March just continually added more load, and finally it reached its tipping point and we had that huge cycle. And you can kind of see this here on the right. Oops, let me go back one. On the right here, where in the early period and mid-period, again, during avalanche years, it's typically above average modeled snowfall, so above average snowfall. But then in the late period, we see above average snowfall, but then a big drop in comparison between avalanche years and non-avalanche years. And then again in March, in this late period, we see big avalanche years happening in those late season storms. So what does this actually mean for operations? So here in Colorado, you guys definitely see wet snow avalanches, typically later in the spring. But in other areas that are not in a continental snow climate, so maybe a little bit warmer, a different type of snowpack, and that's what we're going to take a look at now in Montana and Idaho, which is more of an intermountain snowpack. And in those climates, and well, in general, I should say that recent research has pointed to we're going to see an earlier onset of spring. So, spring is going to be earlier in the year, an earlier onset of wet snow avalanches, and a higher frequency of those wet snow avalanches even midwinter. So what I'm going to talk a little bit about now in this case study is midwinter wet slab avalanches, and I want to be clear that we are talking about midwinter solar-driven, so not rain on snow, and we can't attribute climate change, for example, to any one individual avalanche cycle, just like hurricanes, right? Like we can't say, oh, climate change caused this one hurricane, but what we can say is that the frequency of these cycles, midwinter wet slab cycles, is influenced by climate change. And so, again, we're going to take a look, and this was an unusually warm period in late January. We're talking late January, very early February of last winter. And again, this supports recent evidence of increased melt on dry days throughout the accumulation season, because again, we're not talking about rain on snow. So a little context here of where we are. In Montana, on the left, we're in northwest Montana. The orange dots indicate avalanche occurrences during this cycle. And on the right, we looked at north or south central Idaho. They're both in sort of an intermountain climate. Northwest Montana exhibits maybe more of a maritime influence than south central Idaho. But this is the distribution. We had 68 avalanches in northwest Montana, and that we looked at, and then 11 avalanches in Idaho. And it's important to note that we're at 48 degrees north in Montana, 44 degrees in Idaho. So we're pretty far north in January, so we don't see a lot of sun in general, because we have something called clouds, which you may or may not know of here in Colorado. But we have those, but these weren't cloudy days. These were very sunny days, but the sun angle is still low. So it was an interesting cycle. Let's take a look. All right, a little bit of background context. In January, this is Montana on the left, Idaho on the right. This is just taken from a gridded climate data set from 1900 to 2024. And there is a positive, significant increase in January median temperatures over time, particularly from the 1990s to 2024. And again, that sort of coincides. We did a similar study in the Northern Rockies as to what I presented for Colorado just a few minutes ago. And we found similar changing climate drivers around the late 80s or early 90s. So a pretty steep increase there in the early 90s as well. So these are figures of the meteorological conditions during this cycle. The shading in the background indicates Montana is yellow, Idaho is black, but the shading in the background indicates the duration of these avalanche cycles in all 5 of these panels. So if you look at the temperature there on the left, you can see that in Montana, it was an increase, and it stayed well above freezing for a number of days. In Idaho, it was a very sharp increase, and then it actually dropped below freezing, and then it went back up again. So we did have a freezing night there in Idaho, but in Montana, it stayed well above freezing. And this, I think, influenced the duration of these avalanche cycles. You can see that the avalanche cycles in Idaho was pretty much relegated to 1 day, and then there was one other avalanche later on in that period, that warm period. But in Montana, it lasted for several days. You can see that we did have some precipitation, so a tiny little bit of rain on snow. Observers in the field indicated that it was a very light drizzle, barely perceptible, except when you got back to the truck after riding your sled back and you were soaked. So that's notable because we think that that combined with an extended warm period after that is sort of the perfect recipe for this cycle to happen. So that sort of kicked off the rain, tiny little bit of rain sort of kicked off this cycle, surface melt, and then the warming and whatever radiation we could pull out of the sun with that low sun angle was enough to get things going and to make this cycle happen. This is what the snowpack looked like, right? We can't just think about the weather. We have to consider what the snowpack actually looks like. So on the left, we have sort of the pre-warming dry snowpack, and these are just conceptual snowpacks, hardness there, of course, and then the layers are labeled. But in both locations, they were very similar. In both Montana and Idaho, we had a facet crust combination, mid-pack, and they were relatively close to the surface. And in Montana, it was about 70 to 100 centimeters from the surface and 30 to 100 centimeters from the surface in Idaho. And I actually should note, before I carry on, that so the wet slabs released on the facet crust combination, and by the end of the cycle, the snowpack depth decreased substantially at both locations. And then when we went out to look at the crowns and did crown profiles of some of the avalanches, there was a wet slab above, and then moist to wet facets sitting above that melt freeze crust, but the entire snowpack was wet at that point. All right, so this is in Montana. Started off the cycle with a bang with a D4 avalanche. Observed on the first day of the cycle. 2 separate avalanches observed on southwest and west aspects, and throughout this cycle, they occurred pretty much on southeast, around the southern part of the compass, to southwest and even west aspects. On day 2, the cycle continued, numerous D2s, several D3s, until the end of the cycle. And I sort of inadvertently realized this, but relating, what do they call it in comedy? A callback, I think, but relating to Scotty's talk. This is in a burned area. So just interesting to note that we have these avalanches occurring throughout the terrain. Next. There we go. Okay. So then later on in the cycle, we see fewer avalanches, still in the D2, D3 range. So in Idaho, all of the activity, as I mentioned, occurred in 1 day on January 29th, except for one unintentional trigger on the 31st. And as I mentioned earlier, those crown heights were 30 to 100 centimeters and about 60 to 200 meters wide. The largest recorded slide was on the first day when the majority happened, and that was a D3. And again, as I mentioned earlier, there were fewer avalanches and a much shorter cycle duration in Idaho. And again, likely due to only 1 night without a refreeze during that warming period. All right, so let's place this cycle in the context of, quote, climate normals. And this is a 30-year comparison. So in Montana, you can see there, so Idaho's on the left, Montana on the right. Let's take a look at Montana first here on the right. You can see that in mid-January, it was really, really cold. Well below normal. So these box plots indicate the red is our maximum temperatures, gray is average, and blue is minimum temperatures. So these, and the black lines here in the box plots indicates the median temperature within those 3, and then within the temperature ranges for each day. So mid-January, or early to mid-January, we had a really cold cycle, and it gradually warmed up, to near freezing, hung out there a little bit below freezing for a while, and then it dramatically warmed up. Again, the shading here is the duration of the avalanche cycle. So we go from this really cold period, it warmed up fairly quickly to, again, shortly thereafter, a very warm period, well above normal during that warm period. In Idaho, rather, we had a similar story, but maybe not quite as extreme, where we had a very cold period well below normal, and then it warmed up a bit, and then again during that warm period here, it was well above normal for maximum temperatures even. So, we kind of wanted to know how often has this happened in the past 30 years, so we gathered all the weather data, and we just looked at daily temperature and precipitation conditions that were similar to these 2024 avalanche cycles. We don't have the snowpack data, again, records that go back far enough, so again, we only were limited to analyzing similar conditions, so super simple. And then we wanted to just calculate the frequency of days from January 1st to February 15th that had minimum daily temperatures above 0 with no precip for at least 2 consecutive days. We didn't find any similar instances like this in Idaho at the stations that we examined, and we tried really hard to find some. In Montana, we found 3 other instances of these conditions from nearby MET stations. That would be in 2005, 2015, and 2016. And you can see that temperatures in 2024 in this cycle that I just described were definitely quite a bit warmer. Again, we're looking at max, mean, and min temperatures, quite a bit warmer than those other cycles as well. And again, snowpack definitely played a huge part in the cycle. All right, so to summarize, we had avalanches that occurred southeast all the way around the southern part of the compass to southwest aspects at both middle and upper elevations. So it wasn't like this was just a low elevation cycle. This was at the the highest elevations as well. We see temperature anomalies, so big differences, from average. A rapid change from very cold to very warm. We had the right snowpack, and this contributed to our widespread activity. And these cycles highlight the impacts of midwinter warming with unstable snowpack conditions. So what? What does this all really mean? Again, midwinter warming trends and dramatic temperature swings may lead to more frequent wet slab conditions like this. The interesting thing to note, again, in northern Montana, relatively low radiative input can still produce very large destructive wet slab avalanches if we have the right conditions otherwise. And again, studying case studies like this helps us prepare for future scenarios under a changing climate. So, if you have any questions, I'd be happy to take some if we have time. Thank you.
Thanks, Eric. Packed a lot in there. It's impressive. We probably have time for a couple of quick questions. Ron has one, but maybe we'll start over here.
Oh, we're silencing Ron.
We're not silencing Ron. We're just we're being selective. On this side over here, Rich.
Selective.
Amanda, right there. Yeah.
Hi, thanks, Eric. I was just wondering about your thought process about not including rain on snow events, and if you've looked at those under a different data set.
Sorry, can you repeat the question again?
Yeah, I was wondering what was your thought process behind leaving out rain on snow events, and if you have plans to look at that in a future study.
Yeah, great question, coming from someone from the maritime climate, where there are rain on snow events. Yeah, I think, maritime climate and even us in Northwest Montana, rain on snow events aren't necessarily unusual. And so when they happen and we get wet loose and wet slab avalanches, you're like, yeah, okay, we kind of expect it. But this one was pretty unusual. We don't typically, I haven't seen, and others that I've talked to who've been around for a really long time haven't seen these midwinter warming events that caused such a such a widespread avalanche cycle. And so that was that was sort of our motivation behind it, is like, how often have these actually occurred, and what does that look like? So, we're not trying to be prejudiced against rain on snow events, but we wanted to see how unusual this really was. But yeah, I think the thing about rain on snow events is, like, I think it's hard because getting observations is a bit difficult, because when it's raining, nobody first wants to go out, and then two, it's hard to actually see things. But I think once it clears, then we can get some data. But I think it's always worth looking at long-term records of rain on snow and subsequent avalanche cycles.
Well, I think we need to stop there just to keep on schedule. But thanks a lot, Eric. It was a great talk. Really appreciate it.